seen come out of the Chandra X-ray telescope. So let me give you a little more detail on our panel. Starting at the far end, Dr. Patrick Slane is a senior astrophysicist and the director of the Smithsonian Astrophysical Observatory's Chandra X-ray Center, with a concentration on the aftermath of massive stellar explosions, and he's worked on Chandra since 1988. Welcome, Pat. Commander Eileen Collins is an astronaut and U.S. Air Force pilot who was the first woman to pilot a space shuttle and became the first woman to command a space shuttle mission on STS-93. Welcome, Eileen. Absolute hero. Dr. Kimberly Arcand is a visualization science and emerging technology lead for the Chandra X-ray Observatory, who is a leading expert in studying the perception and comprehension of high-energy data visualization, and she's worked on Chandra since 1988. And last but not least, my good buddy, Katie Coleman. Dr. Katie Coleman is an astronaut, a chemist, and an engineer who served as a mission specialist on STS-93 in 1999. She was the primary crew member for the Chandra deployment. So I'm going to jump right in, and I know our audience is really going to love it if we have a conversation right here. Sorry, I didn't let you have time to clap for Katie. So we're going to have a conversation here tonight, and at the end, we're definitely going to have time for questions. So be thinking of questions you might want to ask. Eileen, I'm going to start with something really basic. How did Chandra get its name, and am I pronouncing that correctly?
Well, I think, yeah, probably any of the four of us could answer that. There was a scientist, Subramanian Chandrasekhar. Hopefully I pronounced his name properly, but he was a very well-loved astrophysicist from the University of Chicago. Way back, he passed away, I believe, in the 1980s. But when we were training for STS-93, the observatory was called AXAF, Advanced X-ray Astrophysics Facility. And NASA had a naming contest. And from around the country, I think schools and people that wanted to submitted proposed names, and NASA selected Chandrasekhar, or Chandra, and that happened while the crew was training. I do want to say that although he was passed away, his wife came to the launch, and we thought that was really great. So that's a short answer, and if anybody, there's probably more to that story.
Yeah, I'd love to add. So you can say the name any way you want. We've heard Chandra, 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 Chandra. And what I will say is when we went down to some of the pre-launch activities, Mrs. Chandra essentially told us what her husband was named as a nickname at the University of Chicago. He preferred Chandra. So she suggested to us to use Chandra for the name of the telescope instead of Chandra, because she thought it would honor him. So we've tried to do that ever since. And we had thousands of entries, but really interestingly, the two entries that won the naming contest, they both became professional astronomers. And I've just always thought that was such a beautiful sort of feedback loop. And I think Chandra would have been proud.
Amazing.
Well, I was going to say, Ellen, that I live up in Western Massachusetts, and someone was supposed to go and give an award to the Chandra team. Well, this was the Advanced X-ray Astrophysics team at the place where they made the mirrors in Danbury. And that person couldn't go, and I got this phone call saying, "Hey, Coleman, you live up there. It's just 2 hours from your house. Can you go down there and give this award?" And I didn't even know barely what it was. And so I went down, I gave this award to the folks that made the mirrors. They gave me a keychain that said AXAF. This is so far before the mission. And then years later, I got assigned to this mission.
Very cool. Pat, I want you to take us back further, because now the mission all of a sudden is existing. So let's go back. How did a space-based X-ray observatory come to be, and how did it come to the Smithsonian?
Yeah, that's a great story, a great question, and a great story. First of all, X-rays don't get through our atmosphere to the ground. So we weren't able to do X-ray astronomy until the space age was upon us, until we could get detectors up above the atmosphere. So in the early 60s, there were some experiments done to look for X-rays from the sun, and they were successful. There was an experiment that was done then by Riccardo Giacconi in 1962, I believe. The detectors are actually in this building, where they looked for X-rays from the sun coming off of the moon. They detected them, and they also detected some completely unknown source that they came back and said, there's something in the direction of the constellation Scorpius. It's an X-ray source. It was the first one they found. Astronomers are brilliant at naming things, so they called it Scorpius X1. And so they invented X-ray astronomy in this way. And a year later, after building something this big that flew up and discovered this, they said, you know, to really do this right, to do X-ray astronomy right, we need a facility that is 30 feet long, that's 4 feet across, that has mirrors with quality that had never been made before, that they didn't even know how to make. And that's what was proposed. Now, that was turned down, probably for good reason. But in the years that followed, subsequent steps were made with larger and larger telescopes until we finally got to Chandra. And Chandra is indeed 30 feet long, 4 feet across. It is essentially the culmination of that early vision.
But why the Smithsonian? I mean, if you could help people understand a little bit, maybe you and Kim, why SAO? Why are we up there? What does SAO do?
Well, I'll start, and maybe Kim has more stories on this front, but Riccardo Giacconi and his team were at a place called American Science and Engineering in Cambridge, Massachusetts, and they were doing all of this work there and decided that coupling with an astrophysics institute as opposed to a science engineering institute was the way to go forward with X-ray astronomy. And so they connected with the Smithsonian Astrophysical Observatory and became the core of the high energy astrophysics division there.
And Giacconi went on to win a Nobel Prize, and he actually took Harvey Tannenbaum, our first director of Chandra, with him. Like, it was a very close relationship. And I think the ability of combining NASA and Smithsonian together is one of the things that makes Chandra so successful.
And Kim, why X-ray astronomy? What are X-ray eyes giving us that we can't get from other parts of the electromagnetic spectrum?
Well, there is a whole universe of light out there, right? If there's anyone here that plays music, for example, think of a piano. If you have just middle C and a couple keys on either side, how beautiful would be the piece of music that you play? It'd be very simple, right? That is equivalent to only having access to visible or optical light. The rest of those 88 keys, they just remain unused. Now, if you add extra keys for X-ray light, extra keys for gamma ray, for radio, for ultraviolet, etc. Now you have the entire piano to be able to play your masterpiece with. Multi-wavelength astronomy is all about understanding which of those keys you need to hit when. And it really makes for, it opens up the symphony of the universe, if you will. And Chandra specifically has this strength in X-rays, where it gets to look at things like exploding stars, areas around black holes, colliding galaxies, blazars, quasars, neutron stars, pulsars. It sounds like science fiction, right? But it's science fact.
Very cool. And Eileen and Katie, I'm wondering, obviously you can get assigned to a lot of different missions as working with the Space Shuttle. But I understand that both of you sort of consider yourselves, and I'm using Eileen's words here, amateur astronomy geeks. And so could you, starting with Eileen and then Katie, how was Chandra a great fit for you as an assignment?
Okay, I grew up in upstate New York. I love upstate New York, but the skies were not as clear as they were in Oklahoma. My first assignment in the Air Force was in central Oklahoma, Enid, Oklahoma Advanced Air Force Base. Out in the middle of nowhere, I discovered the night sky. And I was amazed. I could see the Milky Way. I could see planets. I could see the Pleiades, the tiny little grouping of stars. I'm like, wow, this is really cool. So I bought 2 telescopes. I joined Astronomy Book Club. I subscribed to Astronomy Magazine. Everything back in those days was paper, no internet. And I couldn't get enough of it. Then I started reading cosmology. I just loved astronomy. And I'll just say one thing about Chandra, which was AXAF at the time. As a astronaut, we're always looking at the shuttle manifest, which is a list of the future flights. And I'm going through it and I go, oh, AXAF, what's that? So I found out that it was a science telescope mission. And I'm like, I want to fly that flight. Yeah, it was only 5 days. And, you know, I mean, there were some things about it that were not, I mean, there wasn't an EVA or anything like that. But I go, it's an astronomy flight. And I wanted to get to know more about astronomy, meet the people, the scientists, the astronomers, and that's probably all I want to say about that. But I was so happy when Bob Cabana, who is the chief of the, y'all probably know who Bob Cabana is, he assigned my crew, and I am so happy that I had the opportunity to fly that mission. It's, I mean, what a great opportunity and a great team of people to work with. So thanks for the question.
How about you, Katie?
Well, I've actually never used the words amateur astronomer with reference to me, okay? The night before my first mission, I was still actually Xeroxing this book that basically the person who wrote Curious George, H.A. Ray, she wrote astronomy books, like how to see the stars, for adults and for kids, with really good pictures. This is me. And so I wanted to bring some of those demonstration pictures with me. I live in a really great dark sky place in western Massachusetts, so my husband and I just love to go out and see the stars. But for me, I mean, we don't really get to pick our missions, you know, and Eileen was saying she had a preference, but we don't get to pick. And since it never occurred to me that I might get really a vote, I just didn't worry about that. And I was so excited when Eileen actually called me. I was in Russia working on stuff for station, and as an astronaut, I wanted to go to the space station. I knew you had to be, excel at all sorts of different things, not just science experiments like I did on my first mission. And so the fact that I would be part of the team that deployed this telescope, where you really had to be very operationally oriented, but also it was clear that there were really big teams behind Chandra. There was a brand new mission control that was going to control her. There's mission control in Houston. There's mission control for the rocket on the rear end of Chandra. And it appealed to me to be one of the people that got to help those teams make sure that they're working together. So it was very fun. I loved it.
So I understand that part of preparing to deploy Chandra included all of you getting to see the instrument loaded into the payload bay of Columbia, which I'm so jealous of, including in the vertical while already in the shuttle on the launch pad. What was it like to share that moment? And is it true that it's one of the heaviest payloads ever? So I'm just really curious what, you know, when you're seeing something you worked on or knew about or knew you were going to take it to space and you're seeing it for the last time on Earth?
Well, I'll let Eileen talk about the weight and all, but I just wanted, I'm looking at this picture that you're looking at. So you're seeing the three of us in what we call bunny suits, and right in back of us is Chandra. And the pointy end is actually the part where all of that's where all the instruments are. And if you look up top there's a platform to the left. And so one of the things that I got to do, actually I think that night, was to practice with the actual panel that I would be pushing buttons and pulling switches to control, to check out the telescope. I would do that looking down on the very top of the telescope there. And I saw a mirrored surface there, and I realized that when Chandra was facing us in the back of the payload bay and we're looking out the windows, when she was tilted up to then sort of be launched out over the nose of the shuttle, we would actually see that right in front of us, and our crew would actually be reflected in the image there. So that picture is really special for me to remember being in the high bay.
Yeah, a comment on the weight. I remember Chandra weighed the same as the T-38, which is the aircraft that we used for spaceflight readiness training that all the astronauts flew, so about 12,500 pounds. Chandra. The inertial upper stage, IUS, which was the solid rocket booster built by Boeing that boosted Chandra up to the higher orbit, that weighs about 30,000, weighed about 30,000 pounds. So the whole thing together was the heaviest payload ever flown on a space shuttle. And I will put a caveat of the unclassified flights. I don't know anything about the classified flights, but we were, and that information is, obviously I didn't have access to that, but not only did we have the heaviest payload, but we also had something called an aft center of gravity. And if you look at the photo right now, where it says USA on that white portion, that is in the aft portion of the shuttle payload bay. So most of that weight in the IUS was in the aft. And why is that a concern? So for those of you that know aerodynamics, if you have an aft center of gravity in an airplane, when you're trying to land it, it's a little bit harder to control. It's more pitch sensitive in the pitch axes. So we were concerned of the possibility if we had to bring Chandra back, there were scenarios for that. Thank you, goodness we didn't have to do that. But if we had to bring such a heavy payload back, there were concerns with the landing. So that was really a training issue for me in the shuttle training aircraft. We were able to tweak the software, this is a Gulfstream 2, to, I want to say, duplicate Chandra in the payload bay, coming back to land, heavy, aft center of gravity. And we also trained for the nominal end of mission, which was empty, which is actually the easiest shuttle to land, is the lightweight ones. People sometimes ask me, do the shuttles land differently, like from Columbia to Discovery? No, not really. It was whether or not you had a payload that would make a difference in how it felt when you landed. So that was the heavy. One other thing I want to say about that was, Katie alluded to it, was the clearance in the back. John Young, who was the commander of Apollo 16, was watching over our mission for us. And, bless his soul, he's passed away now, but John was very into safety. He was concerned about the clearance when you tilted that tilt table up. There was only, what was it, Katie, like 4 inches of clearance. And he was afraid that if there was any movement there that we might damage the back of the shuttle. But the engineers convinced us that there was no issue there. And obviously everything went very well. And we're very
And Pat, what was it like to, I'm curious from Pat, what was it like to say goodbye to Chandra when you're knowing that's the last time you're going to lay eyes on it?
Well, first of all, I never saw any real part of Chandra. I did laboratory works to decide what to coat the mirrors with. I worked with reviews of teams that were building different components, but I didn't see any of the flight hardware. I tested some of the mirrors that were in vacuum chambers, so I knew where they were, but I couldn't put my eyes on them. But seeing that whole assembled facility wrapped up in the shuttle and go up, with myself, my colleagues who had worked so long on it, my entire family, it was great. There was some nervousness of, geez, we've just worked this long on this. What if it goes up there and it doesn't work? Or what if it doesn't deploy properly? But most of us felt pretty good about it, and it was a pleasant, sweet experience.
If you could go back to that slide for a sec, the one you had.
Yeah, I'm not sure if we can go back. They can try.
We'll see. So if you're seeing the Chandra in the payload bay, by definition, it's in the vertical, because it was installed in the vertical on the pad. So this is actually sticking straight up and down, and so the nose of the shuttle is at the top of that picture, and the back of the shuttle. And so I just want to explain how it deploys really quick, is that it actually tilts up. It's the nose going to tilt up over the front of the cabin till it's at a really good angle, and that's when, see, this is great. So there it is, tilted up, and there's that mirror that I talked about. And so when everything is ready, that's when and we've checked out and all those things, and that's when I would release, and don't do it yet, the deploy switch, which is sort of like an explosive zipper, where there's springs at the back of the shuttle, or at the back of the inertial upper stage, 5 of them, waiting to push Chandra out. So as soon as that explosive zipper goes, there's nothing holding Chandra and the inertial upper stage there, and these springs push it out over the nose of the shuttle, and Eileen backs away, and I'm sure she'll fill us in on that. But when we were looking at it in the vertical, Michelle Tonini, who was also part of we were the 2 that were charged with deploying the Chandra, and some of the scientists and some of the engineers. And so we're all in the vertical, and we're all like sort of walking on platforms that are out. And it was a truly emotional moment for me just watching them watch the telescope. Because, I mean, knowing that this is the last time anyone's ever going to see it. And I said, well, I promise that I'll take really good care of Chandra, but I can't promise to bring her home.
You were okay with that.
Yeah. Kim, now Chandra is part of the Great Observatories program, which includes Hubble, Compton, Spitzer, and Chandra. Can you talk about the goals of that and why is that? You talked about the piano analogy, but can you talk about this whole NASA Great Observatory program and what multi-wavelength astronomy really brings us?
Yeah, so just like if you're working on something in your house, you need to have the right tool for the job, right? You don't want to hammer something in if you've only got a screwdriver, right? So this idea of multi-wavelength astronomy is making sure you're creating the right tools that will help you answer those questions in those areas of light. And so the Hubble Space Telescope is, of course, iconic, and it is mostly looking in optical or visible light. It also looks a little bit in infrared and a little bit in ultraviolet. And then we had the Compton Gamma Ray Observatory, which has been retired now for quite some time. I don't know the number of years. That was looking in gamma rays. Chandra came for X-rays, and then the Spitzer Space Telescope came for infrared light. And having all of these missions looking at these different kinds of light just lets you answer very different questions, but also work together. So they're kind of like super friends, right? They all have a job to do, and then they work together really, really well. And today, we now have the James Webb Space Telescope, for example, and Chandra will work with telescopes like the James Webb or like telescopes on the ground like the Event Horizon Telescope, for example, to be able to complement looking at different objects. So for example, I think we had the Crab Nebula up earlier, or perhaps another supernova remnant that we could think of like Cassiopeia A. If you're thinking of the debris field of a star that's exploded its guts out all over the place.
This is the crab right here.
This
right?
is the crab right here, exactly. If you're looking at only in optical light, you're going to be seeing material around 10,000 degrees. It's this beautiful filamentary structure, and it's lovely in optical light, for example. But then as soon as you look at it in X-ray light, now you're seeing like these swirling, whirling, more high energy emission. And recently I read an article that kind of likened the X-ray part to tornado chasing here on Earth, right? These really violent things, it sounds very daring. We're much safer than tornado chasers, for sure. We are doing this from the comfort of our computers. But I just kind of loved that idea and that thought. And so Chandra, with the X-ray light, fills in like the center of that debris field where you can see these beautiful rings and these incredible jet structure. And over time, Chandra has even been able to trace all the change in that structure. So again, it's super friends. We need all of these different kinds of telescopes, but each is very specific to the different questions that kind of light has to face.
Pat, can you talk a little bit about the instrument itself and what technologies had to really be developed to make Chandra the amazing telescope that it is?
Yeah, and it follows nicely on what Kim was talking about for the great observatories, because the Compton Gamma Ray Observatory, the Hubble Space Telescope, the Spitzer Infrared Telescope, and Chandra are all indeed unique facilities in different wavelength bands. But there's many different observatories that can operate in these different bands. What's special about these four, and the reason they were called the Great Observatories, is because they were developed very strategically to provide very exquisite capabilities in each one of those bands. And they're large projects. A lot of resources went into them and still go into maintaining the ones that are operating. In the X-ray band, what was really, really crucial is to be able to have mirrors that could make images of the sources that are making X-rays that were very crisp and clear, not blurry. And it's difficult to make telescopes in the X-rays that way. And so one of the key things for Chandra was to take very large cylinders of glass and polish them until they were super smooth and configured to the correct shape so that they would take a pinpoint of X-ray light far away and turn it into a tiny little dot instead of a fuzzy little blob. And that was done miraculously well, and it hasn't been done on any other X-ray telescope since. It remains by far the highest resolution telescope. Then at the back end of it, where our detectors go, we needed cameras that could make use of those spectacular mirrors. And so there were special CCD cameras made that could record those X-ray images, not only recording where the X-rays came in so that we could make a picture of them, but actually recording the energy of each one of the X-rays as it was detected. And so that does two things for us. It allows us to look at what's called a spectrum. We look at a source and we say, how many X-rays of low energy did we get? How many of high energy did we get? It tells us about the physical processes that made the X-rays. In addition, it allows us to take pictures like the crab or like MSH 15-52. Those are just two examples that allow us to look at what the picture looks like in low energy X-rays, high energy X-rays, where they're coming from. It makes us look at the sources and say, why are low energy X-rays coming from here? Why are high energy X-rays coming from here? How does that compare with our models for how these things work? And so those were the capabilities that we really needed for Chandra.
And I'm wondering for each of you, I mean, now this telescope has been around for decades. It's been rewriting astronomy textbooks. And I'm wondering for each of you, when you are telling someone about, I worked on this, or I still work on this amazing mission, what is your favorite example of a discovery or something that Chandra data has helped us to understand? Katie, I'll start with you.
Well, when I was getting ready to deploy the telescope, there was one text, and is it by Seward? It's a really famous X-ray text, and it's a book paperback, you know, and I couldn't read all of it. I didn't understand all of it, but I wanted to read through and understand what these people thought about. And Dr. Steve on the flight was he was our flight engineer, and I asked him. I said, you know, you talk about white dwarfs this way, but then this book talks about that, and he said, what are you reading? And it was actually another that's Dr. Steve right there. It was another astronomy textbook, but for the Seward text, I knew I had to read this book and finish it before the mission, because after we launched Chandra, it would be completely obsolete. You know, so it was really interesting to me that textbook could change. But I asked Steve about something, and he goes, I said, well, I read in this book, white dwarfs do this, and you said that. And he goes, well, when was it published? I said, I don't know, 88 or so. He goes, well, we've learned a lot since 88. I mean, it's 99. And I was like, to me, I mean, I know it may seem really logical, but I just never thought about how textbooks could be wrong and change, and I could be part of that change.
And I hope I'm not stealing Pat's thunder, but I have to go with our classic Cassiopeia A, the supernova remnant, and you can see in the previous composites right in the middle, it was one of the first images we ever released from Chandra, and so I got to work on that data almost immediately, and it was incredibly exciting because the scientists saw that there was a long-sought neutron star, essentially, like this tiny little dot, and Chandra observed it right away. And Cassiopeia A is something that Chandra looks at a lot. It's a calibration target, so it looks at it over and over again. And in each subsequent capture of information, this beautiful buildup of information has given us, essentially, we are able to understand like where the iron is, where the silicon, where the calcium, where the sulfur. And to know that Chandra has looked in such detail at this one supernova remnant and found all of the material that we need for like human DNA, right? That we are literally star stuff, that the iron in our blood and the calcium in our bone and the oxygen that we breathe, it's all there. And Chandra has mapped it out in this extraordinary way. So I always have to go with supernovas because they're beautiful.
Well, Kim says she might have stolen Pat's, but you stole mine.
No.
No, actually,
Apologies.
the first one, there's so many, but the first one that came to mind was Cassiopeia A for me, and the reason is the whole time we were training, we were praying, please work. Please work. So we had done our mission at the end of July of 1999, but we had to wait for the all the, ephemeris and all, check out the Chandra, is it in the right orbit, da-da-da. And we were waiting for first light, and I think it was Steve Hawley that came in the office. It was sometime in mid to late August. He came in and said, "We got a picture, and it's great." And it was like this huge weight off my shoulders, and that was Cassiopeia A. And it was beautiful for all the reasons Kim said. I took these back in the day of slides, but I took that slide around to all the speeches I was making, and I had to be very careful just to use one because I didn't want them to think I was an astronomer because they asked me questions I can't answer. But I used that picture to help inspire school kids and get them interested in astronomy.
So it would be great if I would just jump into other types of astronomy, but since I do work on supernova explosions, I'm going to just go right with where Kim started taking us. Cas-A, which is the object that's at the center of that mosaic that you're looking at now, and I don't know if we have a bigger single picture of it, but that's a supernova explosion. And we all understood that that type of supernova explosion is supposed to form a very compact star called a neutron star at its center. And Cas-A had been looked at with many telescopes. It's seen in the radio. It can be seen in the optical. I was supposed to start singing, right? Clear the room. There we go. There's Cas-A right now. And when Chandra looked at it, suddenly, right there in the middle, none of you have to look too hard to figure out where that neutron star is. It's that little white dot in the middle. And that was great to see. It told us that we could take really, really clear pictures. But if we could look at the picture of the crab that was up before, that's pretty important because most of us knew these young neutron stars that form in these kinds of explosions are rapidly spinning, highly magnetic objects that generate huge voltages like generators when they spin around, and they create massive winds from them, and they're really bright. And it didn't look a thing like the thing in the center of Cassiopeia A. So not only did that first image of Cas-A show us the explosive debris around the supernova remnant, and the compact object in it, it showed us that there's a new type of neutron star that we didn't really know about before.
It's very cool. Kim, can you talk to us a little bit about how is a project like this funded? And over Chandra's history, do you feel like we've gotten our money's worth for it?
I mean, I'm biased, so you're probably asking the wrong person, but Chandra is unique in that NASA funds the mission, and it goes through the Smithsonian Astrophysical Observatory, again, a partnership between those two federal groups, if you will. And as far as Chandra being worth it, I mean, you can't put a price on wonder, right? You can't put a price on figuring out where we come from and where we're going. Those existential questions that humans have been thinking about since humans have existed. And to make it maybe a little bit more practical, in my everyday life, when I'm just going about my non-space business, my life is positively impacted by the telescope that I work for. I didn't know this for years, by the way. I came across some research back in 2016, perhaps, and found all of these incredible spin-off technologies, because what Pat mentioned earlier, how hard it is to create a telescope like Chandra that delivers exquisite resolution of high energy, these photons, right, that are just really hurly-burly out there. It's hard to do that, and technologies had to be created in order just to make Chandra. And then really smart, creative, innovative people came along and said, oh, well, I can use that technology to do something else. And so in our daily lives, if I'm going to a doctor appointment, or I have a mammogram, or I have to get an MRI, those types of medical diagnostics have been improved because of Chandra and or its forebears. Or if we're going to the grocery store or perhaps the pharmacy, that material, those products have been quality controlled because of Chandra and its predecessors. If we are, for example, thinking about, airplane safety and airport security, those issues have also been improved because of Chandra and its forebears. And so there are all of these things that we're doing in our daily life that Chandra has had a positive impact on because it was so hard, right? Like when we do these really hard things out there that are reaching for these really big goals, it ends up benefiting us in so many ways, not just the amazing, there's no price on wonder, but also in very practical, world improving ways.
And Pat, the telescope is still operating. We have a team up in Cambridge operating the telescope today.
It is absolutely operating day and night. It's operating extremely well. We just got done issuing our annual request for proposals for people to ask for things to look at with Chandra. We had 5 times as many requests as we could accommodate. So it's of very high interest, and it's operating right now. Right now, it's taking an observation of a white dwarf star that has material falling on it and creating what are called nova-like explosions, and we're doing a series of coordinated observations with Hubble over the next 2 weeks, looking at it every couple of days and taking spectra of it. So very busy.
And very appropriate for our Chandra namesake that's what Chandra's looking at right now.
Exactly, because the Chandrasekhar limit, which, by the way, you've heard me say Chandra all night. My colleagues from India say that his last name is Chandrasekhar, and so that's how I learned to say it when I was in graduate school. But the Chandrasekhar limit is the maximum mass that the core of a star can have and still be held together as a white dwarf star, which is what is at the center of the image that you're looking at right now. That there's a white dwarf star with material falling down on it, and if it exceeds that amount of mass, if it exceeds the Chandrasekhar limit, it will collapse to a neutron star, or if there's enough mass, to a black hole.
I don't
I'm gonna-
think we
go ahead.
I don't think we mentioned that Chandra was originally, at least what we were told, supposed to work for 5 years total. And we launched it in 1999, which is why we're all like, that it's been working so well for so long and continues to be part of all these different projects.
It was actually required to work for 3 with a goal of 5.
We beat
And
that.
and so we're on 25 now and going extremely well.
We're getting close to the time for questions, but I wanted to go to Eileen and Katie. Both of you have written books, which we see up here on the stage. You know, Eileen, obviously for you, this was a true mission where you could really show yourself as a leader, being the first woman to command a space shuttle, and I'm curious to hear from you a little bit about that, which obviously also you reflect on in your book, and Katie, then for you, you were part of this team, and I know you think really deeply about what it means to be a member of a team and how important that is to you. So I was hoping you could comment on that. But Eileen.
Yeah, well, there's a lot I could say about that. I think the first one is the opportunity to command a space shuttle flight is just, I could only dream of that when I was a little kid. I used to watch Captain Kirk on Star Trek, and I'm like, what if I could do that someday? And, like little kids dream of this kind of thing. And when I had the opportunity myself to command a mission, the first thing I told myself is, it's all about the mission. All the rest of that stuff, doing the PR and, that stuff is fine, but it's all about the mission. So my job as the commander was, first of all, to make sure my crew was trained for the nominal mission as well as any malfunction that could happen. So I'm always asking them, are you comfortable? Do you have enough training? Are you thinking about what could fail? What could fail on the Chandra? What could fail on the IUS? What could fail on the shuttle? Are you, Katie and Michelle, trained for spacewalks? It was always about the mission. Staying in contact with the flight director, the training team, and on and on and on. So I think that focus, the fact that I was the first woman, I said to myself, I can worry about that after the mission. That's not important right now. What's important right now is that we make sure that we have a 100% successful mission. So I think that's the answer to your question. I know you had a second part, but I don't.
Well, I was going to
let Katie handle that one.
Yeah. Now, Katie, just going to you about what, how you think of yourself as a team member, but also the importance of teams and what that means to you.
Well, we've heard a lot about, what we've learned from Chandra, and so it was really clear, actually, from the price tag alone, that it was a really important project. And so it's a mission where it's just bigger than you are, and it's more important than whether you wish you were on a different crew, which I did not, right? But whether you wish one of your crewmates was different, or whether anything that you're thinking about that is not the mission doesn't matter, right? Because the mission is more important. And yet, I think the paradox is that a mission that big can actually depend exactly on you. And as the astronaut who's going to deploy, I felt very much in the middle, but in a wonderful way, between the teams that we're going to deploy. And Chandra was a brand new mission control. It was in the Boston area where my husband lived, so I went up there. If I was in Boston, I'd stop in. They let me park there. That was really important. Anyways, I would find out things like, they talk about the David Brady, the payload officer, and this is the one person in mission control. All those heads that you see, every experiment, every payload goes through one seat, one chair, and David Brady was the lead for that. It's also for all the other experiments on the flight, but that there's one voice in mission control that speaks for the payload, which in this case was Chandra. And basically the people in Cambridge were getting they go, hey, can we do this? No. Can we do this? What if we ask if we could do it this way? No. And they saw David Brady as a person that had little horns coming out of his head. And if you ever met David Brady, and in fact he's always showing up at different things, you would know that there is no one that loved this telescope more and who thought quietly, carefully how he could speak with a voice that the people around him in mission control could hear. And so I went back to Houston and I said, David Brady needs to go on a business trip to Boston. They need to see who he is and how much he cares. And so I loved being part of a mission that had those sorts of things associated with it.
That's great. Before we go to questions, I want to go to Kim last because, when you're talking about something like X-rays, we show these beautiful images that look like art. But I think there's ways to express data that, Kim, you've really pioneered that I'd like you to talk a little bit about this idea of sonification of data.
Oh, sure. It's a topic that I love talking about. This idea that we are capturing data of a different kind of light that humans can't naturally detect, right? X-ray light. That means we are processing it through software, through coding, into the visual representation of it in a light that we can see. But that's not the only way that you can do it. So one of the projects that we've worked on over the past few years is translating that data into sound, particularly for people who are blind or low vision, to be able to experience the high energy universe like I get to experience every day. And that mathematical mapping preserves the scientific authenticity of the data, but then we add sound as an element for exploration. And you can hear Cassiopeia A, our very good friend, the exploded star, Chandra's first light, as it's being sonified right now. It provides you with another experience because sound means a different thing to people. Sound is sticky. You get a song stuck in your head. It calls up memories, right? If you ever think of a song that you had on a road trip and you can never forget that moment. So sound just offers humans another way to process data. And I think because Chandra is a telescope observing a unique kind of light, having a unique way to consider that data and to represent it has been to the benefit of the mission, but also to people around the world, which at least I hope.
And we do have actually a whole album of Chandra images turned into sound. It's really stunning. So I'm going to go to some of the questions from the audience, and these are coming in both from people here, but from people around the country who are watching. We have a question from Brandon, age 9. How long will Chandra stay in outer space, and can it be repaired if needed? So Pat, I'm going to throw that one to you.
Yeah, that's a great question, Brandon. And many people have asked that. Chandra is far away. It's in a very high orbit, and it doesn't get close to our atmosphere. When spacecrafts orbit and get into the outer part of our atmosphere, it sort of drags on them, and it makes them essentially or eventually re-enter the atmosphere and then come down and generally burn up. Chandra is so far away that we haven't been able to propagate out far enough to see a time when it's going to re-enter. We've looked beyond the end of the century, and it won't re-enter by that amount of time. So it will, even if it stops working, just end up in this slow, quiet orbit, watching the world by itself. That means that we can't go fix it. We can't go up to Chandra and make any repairs. It's kind of an amazing fact that after 25 years, without ever having the ability or the need to go up and fix it, that it's still working so spectacularly.
Okay. This is an interesting question. It says, you mentioned how textbooks can become obsolete as we get to discover more and more. With additional missions, do the data from Chandra become obsolete also? So Kim, I think that's an interesting thing to think about, how science data builds.
Yeah, I would say I would take issue with the term obsolete, because there is really no bad data in that way, right? We are capturing moments through different instruments over time. And Chandra, even after it is, eventually retired, hopefully not for a very long time, that data is a record, a valuable record of knowledge and information, kept in an archive where it has that potential value, and then processed by scientists where it has that added value. And so when you have Chandra, for example, with 25 years, and you're able to trace objects changing over time, and you're able to look at things in such new ways, even if there is an amazing replacement that comes down the road, that data is still, again, moments in time. And we use lots of other older missions as well to be able to refer back to things as they were. Because one of the really cool things about astronomy is that it's just time travel, right? Every picture that you've looked at tonight, you're just time traveling with us, right? We are seeing the universe as it was. And so having missions of longevity that can capture things over time is just, to me, a huge strength.
And I think one of the most amazing things for me has been in the past year, especially having had some involvement with the James Webb Space Telescope, is here's Chandra, which is, a 25, let's just say it's a mature telescope. A lot of the images and the breakthroughs you've been seeing come through that are from the James Webb, they're usually a James Webb image combined with a Chandra image, back to this issue of multi-wavelength, multi-messenger astronomy, that Chandra is still as vital today as it was 25 years ago, because these data are now giving us a different window when combined with infrared.
Can I ask, we saw the first images of black holes, and not that Chandra took these images, but wasn't Chandra part of what went into being able to make those images? This is not a question I have every time I give a presentation and show them. I'm like, I don't understand what Chandra did here.
Yeah, it was. The Event Horizon Telescope, which is actually a collection of many different telescopes, made those beautiful images of black holes that most of you have probably seen. The one in the galaxy M87 and the Sag star, the one that's in the center of our own galaxy. And those are mostly radio telescopes, but Chandra participated in all of those campaigns. And one of the important things that it did was to watch the black hole in the center of our galaxy while these other radio telescopes were watching it, to see if there was any flaring activity. That's important in them being able to reconstruct what's happening with the radio emission and narrow multiple possible models that could explain what they're seeing down into the most likely one. So without knowing what's happening in the X-rays, they wouldn't have been able to narrow those models down. Not only that, but those observations are continuing. We'll be doing another one in, I think it's March or maybe April. And now the teams are not just looking at trying to reconstruct that image. We've seen the image now. We know what it looks like, right? Now we need movies. And the way to see how it changes dynamically is to integrate the Chandra data, looking for multiple flares over and over again, and corresponding that with the images so that you can make a multitude of them and pull them together and look at the dynamical behavior of the black hole in our galaxy.
And I think I would just add, if you don't mind, just this idea that for every new question that sort of comes up, Chandra has been able to step up to the plate, right? So it took about 23 years to develop, produce Chandra and get it launched, and then it's now been going for 25 years. So in that time, like exoplanets weren't really a thing when Chandra was about to launch, but Chandra has been able, planets outside of our solar system, but Chandra has been able to study the stars that those exoplanets are orbiting, and they can help us understand the possible habitability of those exoplanets from a telescope that was really being built and designed before exoplanets, like in this illustration, wonderful, were a thing. And that's been the case each time, working with the Event Horizon Telescope, working in multi-messenger astronomy. It's just been amazing that Chandra has been able to step up to the plate every time there's a new tool or a new question.
We do have a question actually on if there's been a change in how you've processed the data over the years, and have there been advances in how you do data processing that helps you get even more out of the telescope?
There have been some advances, certainly since computation capabilities have changed over time. We've used faster computers and better algorithms to make things happen more quickly. But we also continually maintain and study the calibration and performance of all of the instruments and the mirrors. And so as we learn more about their behavior, we will go back and reprocess data to put forth our best calibration and maintain the best knowledge of those data as we can.
We're getting a question on, first of all, a compliment on how beautiful and artistic the images are, which is so absolutely true. And someone is asking if there's an artistic director involved in coloring the images, or is the color purely scientific and functional and what they represent? And so, Kim.
Oh, yeah, that's a great question, because I think we're so used to our phones and we can snap a picture and write, there it is. But images of the universe are not space selfies. They have to be processed into that visual representation to create something like this, the beautiful pillars of creation combining James Webb and Chandra data in this case. And so what we're doing is we're trying to apply what we understand of human vision, for example, the red, green, the blues. We are trying to use the lowest energies in reds, the mediums in greens, and the highest in blues to create that visual representation using a map that really makes sense. But of course, there are lots of times where we have more light than just 3 channels. We have different telescopes that we're adding together. Sometimes we might have something based on the chemical composition of an object versus just energy cuts. And so we'll have to take different approaches. But we've actually studied that. We've studied how people understand and process images to best understand what we can do to make that science-y goodness that's like trapped inside all of those beautiful pixels knowable, experienceable, and also hopefully enjoyable. So I definitely wouldn't say there's an art director, but I think there is an art in the idea of extrapolating out all of that amazing science captured in those images in a way that showcases it and that makes it knowable.
Very cool. Last question, is there something about Chandra that we haven't had time to go into last night that you could give the audience, like if you really want to learn more, go learn more about this topic, whether, we've talked about Cassiopeia A, the Crab Nebula. What would you tell people in the audience who want to learn more? What should they go look at that's going to get them excited?
Well, we should ask the experts, but I just want to say from my point of view, going out talking sometimes, and I'm always going to the website, which is written at like a 6th grade level, which is, for me in astronomy, is the right way to read things. And I think it's very much to the credit of your whole team. I mean, but Kim actually in particular, she'll never tell you that, but the website speaks, it really explains why this is important and why it's interesting and why it was hard. And I think in this year of challenging budgets, where Chandra had to defend itself this year, and I'm thinking that when people go home and want to learn more about Chandra, they're going to read about some of those budget things. And the fact that you and your team have made it so easy to actually visualize, hear, understand that if you leave out this part of the family, you are not going to actually be generating the same meals at the table.
Maybe I just want to say something from, I'm not an astronomer, but for those listeners here, we're all very curious people. That's why you're here. And I would recommend that you share your curiosity with young people, because I find when they see something like this, all ages, your curiosity is piqued, and you're like, I want to learn more. And for kids to take science and math serious in school, sometimes that's a challenge. But if they can see that what they're learning is going to help them maybe discover something someday, learn more about the universe that we live in. And obviously, these are beautiful images. It's, to me, it's art, natural art. Share that curiosity with young people. And I always tell kids, listen to your teacher and do your homework, which sounds very basic, but you can be doing something amazing like this someday.
Well, and this year, they can learn a civics lesson as well, and that's speaking out. A number of these people that are applying for telescope time that are scientists, I actually don't know who exactly are the people that are on the website, but Chandra needed defending this year, and there's a website where I went to learn things. It says, savechandra.org. And because I wanted to learn, I wanted to understand what I was reading in the paper. And I think that understanding that science and funding, and there's a whole picture, and you have to figure out where you're going to find the money to fund everything. But really realizing that, that's why I went to the website, was to learn things, and I think it's a good place to go learn.
If I could, so I think that an important takeaway that really is encapsulated by what we just heard is that advanced civilizations over history, if you look at them, always took time to develop arts and sciences. That's not something that's always possible. Sometimes there's just not the resources to be able to do it, but it's the earmark of important civilizations. And we don't always do it to make better conveyor belts or easier things to make our days go by. We do it to enrich our lives, to stretch ourselves into directions we haven't gone, and to learn things about the way the universe works that rewrites those textbooks that we just heard about. And I think that's what these kinds of facilities do. They put a stamp on the type of society we are. And there's something to be proud of.
And that's a great note to end on. Chris?
Wow. I hate to be the one to bring this to a close, because I think probably all of us could continue to listen and learn from this incredible panel. Thank you, Pat. Thank you, Eileen. Thank you, Kim, Katie, and Ellen for enriching us with your knowledge this evening. And thank you to our friends at Boeing for your generous support of this program. And above all, thanks to all of you for joining us tonight. I hope you will attend or tune in to our final public lecture of the year on October 10th, right here at the Udvar-Hazy Center and streaming online. We will be hosting a panel discussion that looks at stories of sea and air with the U.S. Coast Guard, featuring 3 of the first Black women to break barriers in their field by serving as aviators with the Coast Guard. Free tickets can be reserved on our website. We hope to see you there. And for those of you here in person who would like to purchase a copy of Eileen Collins' book, Through the Glass Ceiling to the Stars, or Katie Coleman's book, Sharing Space, An Astronaut's Guide to Mission, Wonder, and Making Change, you may purchase and get your copies personally signed by the authors at the Welcome Center near the museum's entrance. And with that, I want to again thank you for coming, and our panelists for what has been a really wonderful evening. Thank you for coming. Have a great, wonderful rest of your evening.